Thank you very much. Right, it's a great privilege to address you because I've been described as in many ways, but very rarely as an astronomer. Myself never really, well, the only time I've looked through telescopes is at the sea and at ships. But anyhow, I work for a space agency. Next. Yes, it's called ESA. You probably know what ESA stands for, but to check, E stands for exploration, S stands for science, and A doesn't stand for astronomy. My space agency is what we call in the business a full-service space agency, in that it has to do just about everything you can expect a space agency to do in space, except pure defense activities. Although we do a little bit of things to do with the, let's say, peaceful aspects of defense. We build rockets, we do technology, we have astronauts, we do space science, we look at the Earth, and I have to say, once you're in space, the Earth looks like an astronomical object. And one of the great contributions of the space age is to allow us to treat our Earth as an astronomical object, something you can see from far away, but see in a global manner. Now, there are other ways of breaking down ESA. We do, in fact, do astronomy. In fact, we do extremely serious astronomy. I think it's very important to understand that astronomy is very much part of space, and in a sense, disciplines have changed from being traditional astronomical areas of study to becoming something that's an aspect of space research. Indeed, we're extremely serious about astronomy. In fact, I hardly need to mention it myself, following the previous speaker. Thank you, Jonathan. We are very serious about two particular spacecraft about to be launched, indeed, in April, if there's any doubt about it. They are, in fact, both have contributions from outside Europe, but that's the nature of astronomy. It is a global activity. They're named after people. Herschel, who somebody with my accent claims was a Briton, and Planck, who was certainly a German. I think Herschel was born in Germany also, but it happened to be Hanover, which was at the time unified with England, and he spent his career in England. These two spacecraft are part of a change in the way we do astronomy. First of all, it is wonderful to build telescopes on the ground, and it's wonderful what we've discovered from them. But once mankind with space got above the atmosphere, everything from the stars to the galaxies, even to the Big Bang, looked different simply because of what one could then see. The ability to look across whole new areas of the electromagnetic spectrum. Initially, astronomical spacecraft were relatively close to Earth, and indeed Hubble is really just above us. It's not very far away. But much of the future is being done with deep space astronomical observatories far away from the Earth and far away from the disturbances the Earth brings, looking out straight into the cosmos, and Herschel and Planck are both in this category. I have to say, I was talking yesterday to the people who build the rocket to launch Herschel and Planck. They seem to think that the Herschel-Planck mission lasts about slightly less than 30 minutes. I have to tell you, we won't have these things on station and operating for months after that. They have a long trajectory to follow to their final position for observation out in deep space. And that's indeed what this shows, a sort of halo orbit out at the libation point behind, the Lagrange point behind the Earth. Behind there's the Sun and the Earth, and then the spacecraft performing a loop around the libation point behind the Earth. And this is not the only pair of missions that will populate this space. This is increasingly becoming where space astronomy is going to take place. Let me tell you a little bit about them, although this almost seems unnecessary, given the attention paid to Planck and Herschel around this meeting. And I do urge you not just to go and visit the wonderful Planck Dome outside, provided from French teams on Planck, but also the use of Herschel for educational purposes, represented by the very large truck parked on the other side of this building. Well, in fact, Planck is so excited by the interest taken by the French, it's broken into French there. And really, Planck is about trying not just to look at the hiss left over from the Big Bang, but to look at the high-resolution structure of that hiss and its polarization. 3 missions so far have looked at this. Kobe, famously, then WMAP, as was mentioned by the last speaker, and then later this year, we will start the survey with the most sensitive instrument yet flown, Planck. Really, to decode the earliest thing we can see associated now with our origin in the Big Bang, possibly to simply tell us how matter turned into galaxies, but one suspects also to reassure us or not that we really understand the physics of the universe we live in. Next. Now I come back to Herschel. That's William Herschel. As you probably know, there were actually 3 Herschels associated with astronomy: Caroline, William, and John. Herschel is more or less named after William, except for certain audiences. Herschel discovered infrared light. Of course, he didn't see it, and that's, of course, one of the great lessons of science and astronomy, is you don't always see what it is you're discovering. He deduced there had to be a radiation beyond, with wavelength longer than the red part of the spectrum, because there was heat being carried by radiation from a light source. And this was done in 1800, a very long time ago. And indeed, the idea of infrared radiation now is an almost commonplace thing. Most of us have daily interaction with infrared. And we also know we ourselves glow in the infrared. That's why there are so many infrared detectors about, often to detect people like us. Because radiation is associated with temperature, of course, it means we're looking at the cool universe. And so a universe, those parts of the universe which are at temperatures comparable with those we live on the surface of the Earth. Those of us who also in our past careers have looked at the Earth know that we have to pay a lot of attention to the infrared, because that is the major waveband in which the Earth both receives and emits radiation. Okay, we can, that went a bit fast, but anyhow, we can particularly looked at the formation of things, as was described very ably by my predecessor, with probably more conviction than I can put to it, the formation of stars, the formation of galaxies, and indeed, for those of us who enjoy living on a planet, the formation of planets. Because, ironically, even hot things like galaxies and stars came out of cool material, came out of dust. Okay, next. Now, I want to prove we are serious about astronomy, and it's not just, although we're very excited about the International Year of Astronomy, it's not just the International Year of Astronomy which is behind the fact we're launching 2 major astronomical telescopes this year, Herschel and Planck. Here is the next telescope we will be launching. It's not named after a person, but a goddess, Gaia. And what it does is something, on the face of it, rather prosaic. It's going to produce a 3-dimensional map of our galaxy, the Milky Way. Well, I'm sure we all love the Milky Way, but surely there are more exciting galaxies out there, and indeed Jonathan made that clear, there are indeed. But no, our Milky Way is the one we are closest to because we are indeed part of it. And just like the rest of the universe, we do not see all of the matter in our Milky Way. What Gaia will do is track 1 billion stars in our Milky Way. It will follow them. It will also look at characteristics of those stars, so it'll actually do a lot of stellar astronomy at the same time. But for me, it's a little like nowadays we all have battery-driven watches and so on, but I grew up at a time where you had mechanical watches driven by what was called clockwork and springs. I was always fascinated that a mechanical device could produce a regular motion of anything. And I remember when I was relatively young, probably around 10, I took apart a clock just to see how it all worked, and indeed how you got the regular motion out of something as prosaic as a spring. Well, I'm not sure. I did find out roughly, and indeed I think my parents should have been very pleased that I had this investigative attitude. And in a sense, what we're going to do is look at the clockwork of our galaxy. I have to continue my personal story to say that having deconstructed a clock at the age of 10, I could not figure out how to reconstruct the clock, nor indeed could my parents, which led to some reconstruction of my schedule for a week or 2. However, I'm now at least responsible, not entirely responsible, but partially responsible for deconstructing our galaxy. I promise to make sure that it can be put back together. But that's exactly the purpose of Gaia. It's an enormous task. Go back. Here are the numbers. What Gaia has to chase: 1 billion stars, 1 million to perhaps 10 million resolved galaxies, 500,000 brown dwarfs, 300,000 extrasolar planets, 10 million 200 gravitational lenses, 10 million resolved binaries, 20 million variable stars. It will also provide original tests of general relativity. And you know I'm still fond of the solar system because at least I live there. It will also look at a large amount of objects in the solar system. It can't avoid them. It will see somewhere between 100,000 and 1 million bodies, small bodies in our solar system, near-Earth objects, perhaps even threats to our dear Earth. Astronomers get used to big numbers. We're used to living in a universe that's 15 billion years, 13 billion years old, or whatever. These are very big numbers. Next. This mission is not just a challenge to the optical engineers. It's an enormous challenge to those of us who think it's fun to play with numbers and process data. In its 5-year mission, it will get an uncompressed data volume of around 100 terabytes. And you can imagine just simply getting that stuff down and processing it. It's one thing to get it down. It's another thing to actually make sure we decode it to understand what it's telling us. There are already a large team across Europe and indeed even worldwide, primarily in Europe. This is a particular European obsession, it seems, the taking apart of clocks. And teams are already working towards this grand challenge. For me, this actually will represent an enormous legacy about our home galaxy, our Milky Way. There will be an enormous data mountain, which will be no doubt mined for years for new astronomy, long after the 5-year operations, long after the end of the first survey results. For me, this is truly an astronomical grand challenge and an extraordinary piece of technology. Next. I don't need to say very much about this because, in fact, I wanted just to say a little bit about the fact that amongst the numerous astronomical spacecraft I have to manage, I make a small contribution to Hubble, and indeed, at the other end of the scale, if the galaxy is really our own backyard, then at the same time with Hubble, with the ultra-deep field shown here and discussed by my predecessor at this podium, we go back to the first light, to the earliest things humankind has ever found a way to record by light, to produce a picture of. Next. Of course, that leads me to the other grand challenge that I face. Well, actually, I was just skipping over that grand challenge. Maybe it isn't mine. With NASA, of course, we're very proud to be taking part in a mission which really will be looking back to go beyond where HST has already gone. I think the grand challenge of James Webb is really cosmological, and I have an immense pride in the fact that it will be that our American cousins have entrusted us Europeans with launching this spacecraft. I got a lot of criticism for being willing to spend space science money to launch JWST. Couldn't we build yet another instrument or another spacecraft instead of buying a rocket? I've got news for all astronomers present. You only do space astronomy by getting your telescope into space. And I'm afraid rockets do it. There is no other way we yet know to get up there. I'm very proud of the fact we're trusted by our American colleagues, and I'm even prouder of the fact that when the MIRI instrument is shown by one of my American colleagues, he doesn't bother to tell you it's European. It is, and indeed it was the ticket, the return cost of the ticket that I took from the Americans. If I provided the launch, they would fly MIRI, the mid-infrared instrument, which you saw a picture of just in the previous slide. We don't think of it that way. For us, The two European instruments are just instruments on JWST. JWST is a NASA-led, but a NASA-ESA mission, NASA-ESA Canadian mission, and frankly, it's for the world. And don't imagine otherwise. It's something I think we're all immensely proud to be involved in. And one of the glories of astronomy is that it is for mankind as a whole, because whether we like it or not, we all came out of that cosmic dust. Next. Okay, this is a field. It's a pretty ordinary looking field, rather flat. As some of you may immediately recognize that it's in Hanover, in Germany. I guess not so far from where Herschel was born. And it is actually the site of a gravitational wave observatory. The scale of the observatory, you can just detect the right angular structure there. The L-shaped, backwards L-shaped structure is actually a laser system spreading over kilometers to try and detect the passage of gravitational waves through the Earth. Gravitational waves, we know they're there, surely, because we've seen their effect, their hidden effect, like infrared light, their hidden effect in things like the millisecond pulsar, the slowing down of pulsars. Has to be a radiation that must be gravitational waves. So we know they're there. We've never directly detected them. They're fascinating things to detect because they have a fundamental quadrupolar signature, which I was trying to do with my hands and I can't coordinate well enough to demonstrate, but you go down in one direction and out at the same time in the other. And here you can see, to build a gravity wave detector on the surface of the Earth, you need a lot of real estate. It's true it's thin in one direction, but it's very long in the other. There's a logic that says you cannot expand beyond this. There's a logic that tells you to go beyond this, you've got to get off the planet. So, next slide. We're going to do that with another mission that will be launched not too distant future. It's not going to directly detect gravitational waves. It will show whether free-falling masses follow a geodesic, which is, of course, fundamental philosophy, but it will, at the same time, lead the way to the next slide. LISA Pathfinder will lead to a grand observatory out in deep space to be the first true observatory of gravitational waves, LISA. Next. I want to remind you that once upon a time, the solar system was an object of interest for astronomers. In fact, I think most astronomers are interested in the solar system, if only as a place where you can build telescopes or fly them. Titan, one of the classical early discoveries of the telescope age. Now it's something else. It's a place we've been to. This is an image, a composite image of the landing site of Huygens on Titan. The discipline is still the same, but the nature of our capacity has moved us back from telescopes to actually scratching and sniffing on the surface of things. Next, Mars. Believe it or not, this picture, which comes from the 19th century, it's a drawing from the 19th century by Schiaparelli, I took from a book I had as a boy in 1954. This was what Mars looked like in a child's book. Next. This is what Mars looks like through a telescope. I think it's the Hubble telescope. Beautiful. However, next. We've got to also realize we can go out there, and that is one of the great attributes that space has brought to the world of astronomy, actually going out there. And so I close with next, quickly taking you to Mars. The images here are reconstructed directly from data taken by the high-resolution stereo camera on Mars Express. It may be fun to go down and scratch and sniff on the surface of Mars, and we Europeans are going to do it, just like the Americans have already. I'm sorry about the German, but it's probably time someone said some German. This is a German camera, I have to say. For me, this is as if we were flying over the surface of Mars, using as the basis of the image the images, the three-dimensional images taken by the stereo camera. For me, I could watch this for hours. Of course, I could go on talking to you for hours, but I realize I should not. So I will stop, but I will let the pictures play. Thank you very much.